So we're at an interesting part of the course, and studying graph theory becomes really kind of different right now. So just to remind you, what if I want a circuit that contains all edges, that contains all the edges. Well, what condition? What condition do I have?
All but two vertices have to be even degree.
Okay, but I want a circuit which is closed.
Oh, then all of them have to be even degree.
And
it's connected.
Okay, so to have a circuit, we know precisely if all degrees are even and the graph and G is connected, then there's what's called, of course, an Eulerian circuit. Open and shut, you don't have to do, I won't say you don't have to do much work. What do you have to do? You have to check to make sure the graph is connected, which is typically not hard. As long as there aren't 1,000 points, you probably could do that pretty easily. And then you have to make sure that all the degrees are even. So this is a pretty easy condition to find. Connected in even degrees. So for a trail containing all the edges. Okay, so not necessarily a closed trail. Now what's the condition?
Now two of the vertices can be
And?
odd, and it still has to be
It
connected.
still has to be connected. I know that, we know the connectedness, stop asking us about it. But sometimes you just take it for granted, and then you realize that a graph is not connected. It becomes pretty difficult. So this is, it's open and shut. It's easy to check these conditions. It's maybe not easy if I have a graph on 10,000 vertices. And we haven't really talked about anything related to algorithms or actually how you check these things. But if we have a graph, it's not necessarily difficult to determine whether the graph is connected. And then, in fact, it's just numeric to decide whether the degrees are odd or even. Okay, and again, the trail, if there are two odd vertices, you can tell me even more.
The trail will end and begin at those two.
So that's the starting and ending place. Okay. What about, I want a cycle that contains all the vertices. Okay, so two things I'm going to underline. Cycle, different than circuit. Cycle means what? It's a cycle. Go ahead. What was that? I'm sorry. A closed path. Okay, a closed path. And in particular, no vertex is repeated. Of course, if no vertex is repeated, then no edge can be repeated. Okay, so that comes for free. It sounds just like this Eulerian thing. What conditions will tell us that a graph contains a cycle that contains all the vertices? Okay, so I think I gave you some of these problems to look at over the weekend. On page 206, 207, 208, and PN cross PM. Alphabetical, PM cross PM. Okay, and the question is, which of these graphs contain a cycle that contains all the vertices? And we did name it. Such a closed path with no vertex repeated that contains all the vertices is called a Hamiltonian, after mathematician, actually a physicist in the 1850s, Hamiltonian graph. Or the cycle itself is called a Hamiltonian cycle. Okay, so did you look at these? Did you look at any of these graphs on page between 210 and 211? It's been a long weekend, huh? Well, hearing none, I'd like you at least to take a minute and tell me, I'm going to look at page 211, number 2, determine which m by n rectangular grids, pm square pn, so that's the product of pm and pn, and here's what they look like for small values. For what values of m and n is the graph Hamiltonian? Take a minute, talk amongst your table mates. Which ones are Hamiltonian? There you go. But in general, PM, you know the answer. Okay.
A is Hamiltonian, B is 这不全是吗？
一是吗？没有什么是。
是啊，哎呀，你不是说了吗 ？Vertices 吗？需要。
但是它需要是一个 closed path，还不能 repeat vertices。第一个应该不是。第三个，第四个。
Nothing personal. I'm glad to know that.
这样折下来，折上去，折下来，这样回去。
What'd you get?
Pam, if you come in shaved,
Yeah.
it's just that's
Yeah.
not going to be good.
So I think it's if one of them is even.
Right.
And that would certainly
Assuming
follow.
the first one's 30, then it has
Well,
to be.
I think we could extend that. I mean, obviously, I don't like written out a proof or anything like that, but it's basically like, if it's so if they're both even, then you can just
我发现它只要是
then you can just or well I guess all the way down. So that seems pretty reasonable.
双数它就可
I'm
以。
sure we could write that out by induction a little bit more formally than that picture. But and then if
Number of the vertices.
yeah, so then whatever. So if this is even, but this is odd, then you can just kind of come up here and
Right.
however many odd things and however many even things across you want to go.
可是你看它第二个图，它这个也是 vertices，这个 vertices 它也是单数的。
只有是单数的。
我觉得也是。就是 m 和 n 里面必须有一个 m 乘 n 是需要是双数，不 m 乘 n 是单数。
必须要有一个是双数，所以就是确实就是。
Got it?
I think so. So if one of them is even,
One of them is even.
yeah, then a path, then it's Hamiltonian.
Okay, so here's a conjecture. If m or n is even, if at least one of m or n is even, then Hamiltonian. Okay, it's a conjecture. Can you prove that or disprove it? Works for two.
So are we saying if and only if?
No, I don't know. I don't know. Are we saying if and only if?
I will conjecture that. Conject it.
So how might you attack this problem? So I'm going to get back and answer this question right now. How would you attack this problem? Let me okay, so you're gonna do this by induction, or so maybe we would induct on this and then add 2 rows and 2 columns. No, 2 rows, just 2 rows. Because if I can do it, if this is Hamiltonian, the conjecture is maybe this is Hamiltonian, maybe. But let me go back to if and only if. Is this if and only if? So, what about? Let me give you 2-7. P2. Sorry, box. I'm never going to get there. P2 cross P2. The product of P2 and P7. So 1, 2, 3, 4, 6, 7. So the product of P2 and P7 is this. One looks pretty odd to me. Is one of them odd?
One is odd.
One is odd.
Mm-hmm.
Is it Hamiltonian?
Yep.
Looks pretty Hamiltonian to me. Okay, so at least one of M and N is even. Oh, maybe that's why I wrote this down. Okay, so let's start with the. Wait a second. We can't have 1 by 1. Doesn't make sense. What's a 1 by 1 grid? Not very interesting. It's one vertex. It's not very interesting, and it's not Hamiltonian. This is not Hamiltonian. This would not contain a Hamiltonian. It doesn't contain any cycles. Okay, 2 by 2. That's okay. What about 3 by 3? Can someone prove that P3 cross P3 is not Hamiltonian? Just make sure we know what P3 cross P3 is. So there was one result that we talked about last Thursday that maybe will be helpful. If it is Hamiltonian, what can you tell me about the edges at vertices of degree 2? If it's going to be Hamiltonian, then, and you have a vertex of degree 2, then these edges must be used. Okay, and just to make sure, I'm looking at these vertices of degree 2. Okay, and if I have to use those 8 edges, then in fact I can't find a Hamiltonian cycle. Is that clear? Okay, so does the same proof work for what's next? 3 by 4. It's going to take a long time to get them all this way, but
如果他想要把这线索连起来的话，因为这个点来说，你一定需要知道这个点一定要知道这个点需要知道，这样的话会有点是所以这个。对，光连这对吧？
Come on, it's almost like a game, right? Now, last week we knew something, we talked about something, if it's Hamiltonian, what about vertices at degree 2? If it's Hamiltonian, what can you tell me about vertices at degree 2? Contained on the cycle. Okay, so notice in a graph like this, that means that these edges have to be, if it's Hamiltonian, these edges have to be used. So, I mean, that's almost all the vertices. I only have those, kind of those two vertices in the middle. So it's like, can you connect the, sorry, this doesn't leave this room. Can you connect the dots? Yeah. How would I do it?
Are you gonna just ask me to draw the pattern?
Do you want to come up, or do you want to just tell me what to do?
Sure, so the top middle one is where I started, above that. Yeah, now to the right, down, down.
Okay, so I'm going to include this edge. Now you got to include all these, right?
Yeah.
Now what?
And now to your right, up, to the left, yeah.
Okay. 3 by 5. I'm just going to do one or two more, and then the homework is going to be the not to hand in homework, just because I'm pretty bad at grading homework these days. It's 3 by 5 Hamiltonian. So 3 by 4, check. 3 by 3, no. 3 by 5. Talk amongst yourselves. I don't even hear any pencil scratching.
这个点排比是 A。
必须要连这边和这个，这个点必须要连这个和这个，这个点必须要
It's only got 15 points.
这个点必须要连这个，
那不需要连这三个。
这个点必须要连这
Kind of
个，
a similar
就你要
perspective.
至少要连这三个其中的两
You
个
got，
所以你就
the edges that
你
you
就
need
把
to
这
do.
你就把这三个钱画出来，这三个钱画出来，
And
这两
seeing
个
what
画出来，这两个画
vertices
出来，那
that
这两个
you
点，
end up with,
我觉得就是这个道理，
like across in the middle.
就是绕
对啊，
And you
回
have
来。
to hit every vertex in there.
就
我觉得
但是你
绕
这么
回去
串，这个地方你这么
You can't do without repeating.
所以这个点必须连这三个，这个点咱们必须连这三个，你全连上。
Yeah, it certainly doesn't seem like it. I think I would struggle proving this, but
所以
That's
你这
where
画出
I'm
来，相当于是第一题的两个重复嘛，所以这中间两个依旧是没有的问
see
题。
that in proof.
right.
嗯，
Like you said, though, it's pretty easy to figure out a way to do it.
Right.
Right.
Right. And then to inductively say, let's add on 2 more rows or 2 columns.
我觉得这个就没有
That seems pretty
这
reasonable.
个
But
除了你就画一遍。
画没再画出来，
哎，你今天怎么来上课？
就疯
我以为要拿试卷，结果他不拿，我就很气
你看这10点多个，
老师就是这样专制。这些
我已经很久没有听他正常的语速上过课了。
你一直在看他的2倍速。
是的，真的，他今天正常语速我都听不惯，好奇怪啊！他竟然会
okay, I
正
guess
常
we
的说
could
话。
say.
哎，这都被录下来了，我靠！
I mean, you can pick whatever point you want as your start, right?
Right,
Because you
that's-
can
Doesn't
start
matter.
there. So then if we just pick this as our starting point,
我猜。但是今天还是
I guess we'd have to say that
有些22号
okay, this will have to be used.
明天20号，明天可能，明天我们20号，
I mean, I guess we could just start breaking this up into
所以
cases.
明
You know,
天晚上
we know that both of these will not be used,
把那个偷偷下来，偷偷
right? Because
Right.
you can't have
You can
3
only
going,
pick one.
right? So I guess we could just do case 1 and case 2, and then
我
just
始终
start.
觉得这个操作一定
and then
是
start
很
going to
重要
town.
但是
Right. The problem is it breaks down when you get a larger grid.
Yeah, I don't know. Yeah, it would become very complicated very quickly. I don't know that we could do this by induction. This would be good for maybe this case.
Right. Like on a small scale.
Yeah.
来画，
影子死2次，
可以为说这个命理记录。
没有逼格，影子死2次是什么意思？
是 no way to prove it。
话题转体快。
I wonder if you could say like
就说我们在聊完这些种之后，after we finish，然后
if
中
you've
间
got
剩下
a
的就
subgraph
然后 B 或 A 里头
that
不是一个汉密尔顿，
because I'm looking at
正好是一个 A。
3x4 that was
中间这
Hamiltonian.
个无论如何都不可能，
嗯
不用说我
And
们规定必须要
you
从这4个角出来。
Basically ignore the edges that you know have to be in there,
Mhm.
and you're left with that box on the bottom.
Yeah, we're left with this.
可以啊。这个其实可以。
I guess we should even.
这个转移话题。
Okay, any conjectures?
And
Any thoughts on this?
Yeah. So the 4 vertices on the 4 corner. So after we just since they only have 2 edges, so we know those 2 edges must be
Okay,
part of the
okay, so just like we started before,
yes.
these, those edges must be included.
Yes. And we notice that there is a graph A in the middle. So
This, let's see, so these 9 vertices or just these 5 vertices? Which one?
there's 9 vertices.
9 vertices.
Yes, they are just the graph A, and we know the A is not the Hamilton. It's,
Is that enough to,
I think so.
okay, so this is P3 cross P3,
Mhm.
the product of two P3s, and that's not Hamiltonian. Is that enough to show that the whole thing is not Hamiltonian? No. Because we would do the same thing and then this would be left? Okay, so I mean, we're going to come back to this. The book gives you lots of, you know, I like the iPads. You know, you may want to play with this. We got a P3 cross P6, P3, P5, pretty easy. So I want you to look at the problems on page 211. So we've done, by the way, we haven't really answered this. We haven't really answered it, and I hope I get an answer tomorrow. But, sorry, Thursday. You can give me an answer tomorrow also. So on page 211, you have some products. How does it change? So I would like you to look at, on page 211, 5.2.3 point G, parentheses G. Again, 5.2.3 G. It's almost, that's almost a 4 by 5. So first what I'd like you to think about is P4 cross P5, feed P4, the product with P5, and I'll just put a question mark, is that Hamiltonian? And then if I just take one vertex somewhere, and I put this little square in there, so I take 1 point and I make it into 4 points, how does that mess things up? Or maybe that makes things better. Okay, so I'd like you to think about that as we move on. Now, what's really strange is, you know, for Eulerian, I know I have an easy condition I can determine. For Hamiltonian, maybe that's not so easy. Okay, so let's go back to this graph over here. This was from page something. So this graph was from page 208. And one thing that the authors notice is when I remove these 2 points, when I remove those 2 points, there are 3 pieces that remain. So I'm gonna generalize. I have 2 points and 3 pieces. I don't know what the edges are, but is there any way that this graph can be Hamiltonian? Is there any way that there is a cycle that contains all the vertices? I don't even care what's in here. Let's just make them big, complete pieces. So, and if it was really Hamiltonian, it doesn't matter where I would start the cycle. So let's imagine that I start at one of these vertices. Okay, and this vertex is not adjacent to this one, so I'd have to go down to, let's say, this piece right here. Now, maybe we're able to pick up all the vertices in here. The only place that I can go is I can go back here, and that's a problem, right? What's wrong with that? Do what? We would be that would be done. That would form a cycle, and we'd be done. Okay, so the only other possibility is that I come here, and then I can go to one of these two. Doesn't matter which one. And now we're stuck. We're stuck. So one condition that's necessary for a graph to be Hamiltonian, necessary, not necessarily sufficient, necessary, is what? For every set S, so this is my set S. What can you tell me about what happens in G minus S? When would there be a problem in this graph? What can you tell me about G minus S where there's a problem? And look at the example. So So they're independent. So if every set S, G minus S, the number of components in G minus, the number of components, let's see, how can I write this? Number of components in G minus S. Well, when do I have a problem? When the number of components is, okay, so greater than the order of S. So if the number of components is less than or equal to the order of S, sorry, let's make that clearer. If the number of components in G minus S is less than the order of S, nope, that's not right. If the number of components in G minus S, G minus S, is greater than the number of elements in S, then it's not Hamiltonian. Then G is not Hamiltonian. So, and this, this is when, and let me sort of talk about why we might want a Hamiltonian cycle, why we might want a cycle. So if we're thinking about an application problem, and this book really avoids talking about any applications, which is unfortunate. But if you look at most other books, they talk about transportation networks. They talk about actually traversing through a graph and having certain properties on the trail that you follow. What I might want is a graph, and now think about the streets in downtown Denver. And I want to traverse I want to be able to get to each corner exactly once and return back to the same spot I started. So let's go from Larimer. Let's see, from Larimer, how for Market, Larimer, then what's next? Lawrence, Arapahoe, one more. What's after Arapahoe? What is Curtis? Curtis? So, one of those, Champa, yeah, it's a C street. Okay, so we can think about the streets of downtown Denver. So let's just look at 5 streets, whatever they are, and let's imagine here's the convention center. And what's nice is, we don't even have to worry about the names, right? This is 14th Street, 15th Street, 16th Street, and 17th Street. And you're at the convention center, you're visiting Denver, and you want to see as much of Denver as possible. Can you traverse in this case, 25 points of interest, right? I've got 5 points of interest on 5 different streets, so I think there's 25 points. Can you traverse the 25 points of interest and end back up at the convention center where the convention is going, and you're there now to see the next speaker because you've seen the 25 points of interest? Can you do that and traverse, visit each vertex exactly once? Okay, so this idea of Hamiltonian becomes important when we're talking about transportation, when we're talking about traversing a set of vertices in some fashion so that I get to all the points. So I want a cycle that contains all the vertices. And this turns out to be a much harder problem than deciding if there is a closed trail, that contains all the edges. One more time, if I want a closed trail that contains all the edges, if and only if, that fill in the blank. You fill in the blank. Someone fill in the blank. One more time. A closed trail that traverses. So I want to not only visit each vertex, I want to actually traverse each street. So what's necessary for me to be able to traverse each little piece of downtown? I know there are good shops that I want to visit. I don't know, but it's got to be connected. Well, that's a good start. And at most 2 odd vertices. And if I have no odd vertices, I can start and end at the same place. And if I have exactly 2 odd vertices, then I can start at one and end at the other. And connect it, right? We'll assume that the streets are connected. This problem is easy. It's an easy look, it's an easy check, but being able to find a Hamiltonian cycle is not so easy. Okay? And we're gonna look at some conditions that tell us when a graph is Hamiltonian. So let me put out something for you. Okay, so you know, a grid, and I don't know how big, you know, just imagine that it's a very big grid. You know, it looks like there's a lot of edges, bless you, but you know, here I have m times n vertices, and actually I don't have too many edges in this graph. So imagine that this is Pm cross Pn. So each column has, let's say, m edges, and there are n of them. So how many edges are in this whole graph, this grid?
M times n.
And did someone say m times n? Yeah, that sounds right. M times n. How many edges are in the complete graph? How many vertices does it have? It's not a trick question. M times n. How many edges would be in the complete graph? M times n, choose 2. That's a pretty large number compared to, what do we say, m times n, the number of edges. M times n, choose 2 is like m times n squared over 2. Okay, so it's a pretty large number. Okay, so there's a lot of edges. If it was the complete graph, it'd be easy to decide. So maybe one of the things that I need to do is, if the graph has enough edges, maybe the graph is Hamiltonian. Notice, throwing more edges into an Eulerian graph doesn't necessarily make it Eulerian. Okay, why not? Okay, one more time. I have an Eulerian graph, and I throw one more edge in. I don't care where the edge goes, I just put one more edge in. That would make, if all the vertices had even degree before, then the extra edge would make 2 odd vertices. And maybe I would know now that I can have a traverse each of the edges exactly once, starting and ending at these 2 odd vertices. But what if I add 7 edges? You don't know, right? You could really mess things up with 7 edges. And when I say mess things up, you can make even vertices of even degree have odd degree, and vertices with odd degree can make even. So we really don't know what an addition of edges to an Eulerian graph is going to do. So what I want you to do is I want you to think about, when at your tables, I want you to think about, does it help for a graph to be Hamiltonian? Remember, a Hamiltonian means a cycle that goes through every point exactly once. Of course, that's redundant because that's what a cycle means. Okay, so does it help to have more edges? And in particular, can you give me a graph that has a lot of edges? You decide what a lot of edges means. I mean, these graphs, right, PM cross PN doesn't have a lot of edges, right? The max degree, imagine M is let's look at P100 cross P100. It has what? It has 10,000 vertices. Has 10,000 vertices. And the highest degree is what? P100 cross P100. Highest degree is?
4.
4. So, in fact, let's just give it a rough count. Let's imagine that 4 times 10,000, we've counted every edge twice. So 4 times 10,000 is 40,000 over 2 is 20,000. 20,000 edges versus what? 2,000 choose 2. 2,000 choose 2 would be the complete graph on 2,000 vertices. 2,000 choose 2 is a pretty large number. It starts with 2,000 times 1,999. And then you divide some things out. It's pretty large. In fact, I think it's 1,999,000 edges. That's a lot of edges. Okay? But the more edges I put in, it certainly has to be, you would hope that if I put a lot of edges in, the graph is going to be Hamiltonian. Okay, so what I want you to do is, I would like you to think about, can you come up with a graph that has a lot of edges and is not Hamiltonian? And let me make it clear, if you're going to give me a complete graph, certainly a complete graph has a lot of edges, but it certainly is Hamiltonian. But maybe that's a hint. No, a complete graph by itself. A complete graph by itself, of course, is Hamiltonian. Okay, so let's start with a K100 and add one more point. That's a lot of edges, right? I just want to make sure you understand. K100 has 100 choose 2 edges. 100 choose 2 edges is what? 100 times 50? So that's what? 5,000 edges? That's like punishment. Draw a K100. It's like punishment. Okay, that's a lot of edges. Certainly that's Hamiltonian. But I claim I can add very few more edges and the graph is not Hamiltonian. Oh, by the way, I have to add more vertices as well.
So I would say any graph with a lot of edges is Hamiltonian. I know I'm very loosely stating how much a lot is, but maybe we could define a lot. Well, any complete graph is Hamiltonian, right? Yeah. So any graph of order n, there's going to be some number n where you get that many edges. It's Hamiltonian. It has to be, right? I mean, there's got to be some number, right? Because once you get to complete, then it's.
So I'm going to repeat the question. So start with K100. You can add some vertices. K100 has a lot of edges. Add some vertices, and maybe not too many edges, and make the graph not Hamiltonian. K100, I mean, basically you start at any vertex, close your eyes and go any way you want, and as long as you don't repeat vertices, you'll get back to the start. K100. Everybody understands the complete graph on 100. Add some vertices and some edges so that the graph is not Hamiltonian.
这是所谓的 add sign， 就是在这个 K100。
This is a loaded question.
加一个别的，
I think you're working too hard.
随便加一个，然后这一条线就没了，你怎么着你也不能回答。
Okay, let me cut to the chase. So if I have K100 and I add a vertex, is this graph Hamiltonian? No, because there's no way. It's not connected. Okay, so connected. Is this Hamiltonian? But it's connected. Maybe? No, why not? Because that vertex only has degree 1. You can only go out or in, never the other one. Okay, so this is not Hamiltonian. Is this Hamiltonian? Yeah, of course. In here, once you get in here, you can do essentially anything. Right, so... So here's my next challenge. By the way, the challenge is we have to build up the challenges. You have to tell me PM cross PN. When is PM cross PN Hamiltonian? Okay, and I'm gonna extend the challenge. PM cross PN means that there's a Hamiltonian cycle. Hamiltonian cycle means cycle. It's closed, connected.
Contains all
It
vertices.
contains all the vertices. Okay, so Hamiltonian means a Hamiltonian cycle when for what M and N is a Hamiltonian, and they don't mention it in the book, but I like to look at what's called traceable, which means that there's maybe not a Hamiltonian cycle, but there's a path. So I can start just like a Eulerian trail that doesn't start and end at the same point. I can start at some point, go visit every vertex, and end at another point. I don't care which point it is. Doesn't have to be connected, doesn't have to be adjacent. I can start at some point X and end at some point Y and have visited every other vertex. That's the idea of traceable. So conquest 1 is tell me what values of M and N make PM cross PN Hamiltonian cycle, traceable, meaning there's a Hamiltonian trail, Hamiltonian path. Okay. Okay, so again, these are sparse graphs. Okay, sparse meaning not too many edges. Let's talk. Let's see. It's got M times N edges, and the possibility is it's got M times N choose 2 edges. M times N versus M plus N essentially squared. Okay, so that's not very large compared to how many edges I can have on M plus N vertices. Sorry, N times N vertices. So the next challenge is find a graph with a lot of edges that's not Hamiltonian, not H. And when I say a lot of edges, okay, so let's talk about what I mean by a lot. If I have N vertices, the greatest number of edges that I can have is what? N vertices, N choose 2. That's the complete graph. Every pair of vertices are joined. Can you find a graph that's close to N choose 2 that's not Hamiltonian? Okay, I'm going to make it a little bit harder. Okay, can you find a graph that has approximately every vertex has degree N over 2, half the number of edges, half the number of vertices. So can you find a graph that has degree about N over 2 that's not Hamiltonian? Okay, does everybody understand the challenges? Okay, go. No, not go. I mean, solve it.
最多 ages 是按照 complete age， 它让你找一个基本 and choose two， 但是不是 complete， 不是很多。或者是让你说，可能你拿掉1-2个这个图变得不是很多。
Allison? Dylan?
右边这个点，然后这两个发点都是
V?
这个不是汉密托尼，汉密托尼是比较从日从开始的，你都是你们随便找一个点，从这个点开始，你没发让它回到原点，因为
John Wen? Okay, Yang Chen? Yeah. John Wen?
Well, it's just entries.
Pim? Oh, it got awful quiet. Selma?
汉密托尼的 graph 是从哪里开始？你都能找到。
Sija? Sija Lu? Sija? She's not here. Okay. Jin Wen?
我觉得这个是任意一个
I know you all have an English name. You just are making this hard on me, aren't you?
它都不是一个那什么。我猜，大概。
John
What
Wei
do you think
Wang?
about these?
Well, for the second one,
The traceable one? Or you mean,
Yanning
are you
Song?
doing the one down here?
the one that's not Hamiltonian.
Yeah.
Vicky?
I don't know, I'm just trying to figure out. Because, like, my first thought was trying to make, I guess, a
Kishi Shan?
cut edge somewhere. I
Can
can't
you
really do
write
that
any smaller?
If it has to be a pretty
Did you,
simple
are you past, you didn't say yes quick enough.
So I drew it out with, so if n is 6, then 6 choose 2 is 15. So that means
Rui?
average vertex degree
Rui
has to be at
Zheng?
least 2.5. So here we have
Ben?
2, 2, 3, 3, 2, 2. Okay, so this one's less than 2.5, and it is not Hamiltonian. This is greater than 2.5, and it is Hamiltonian. So,
Jinyan Lui?
I mean, I
About,
know that's
Jinyan
not proof
Liu.
because this is one example, and we're supposed to do it about infinite. But as an example, this one,
Yeah, I think so.
if you want to
She's
say
in
that if
Yuzhen Gao?
this is greater than the degree
That's
sum,
not even close.
it's Hamiltonian.
You have an English name, don't
If it's
you?
less than the degree sum, it's not necessarily Hamiltonian.
Okay. Everybody get
I
one
drew
that's
out one
supposed to get
example
one?
that supports that.
Preferably their own. Okay.
Oh,
Okay.
I didn't get one. I had emailed it to you though.
Well, you didn't give me that.
I emailed it to you.
Did you email it?
Yeah.
Oh, okay. I'll check.
Okay.
Okay. Okay, how about a dense graph that's not Hamiltonian? All right, what do we mean by dense graph? How about a graph that has a lot of edges that's not Hamiltonian? And what I want you to do is I want you to, when we talk about a lot of edges, how many edges does PM cross PN have versus how many edges does KM plus N have? What's the difference? What's the difference between PM cross PN, which is M times N vertices, and then KM times N? What's the difference? I mean, is that a large number of edges that are missing? Someone say yes.
Yes.
It's a pretty large number. If M and N are big, like 10, then it's quite a lot of edges. Okay, and now you need to be thinking about edges probably help to find a Hamiltonian graph. Okay, so I'm going to give it to you one more time. Kn is Hamiltonian. Everybody, is that clear? I mean, you don't even have to think about it. Label the vertices 1, 2, 3, 4, 5, 6, 7, 8, n. Go from 1 to 2, 2 to 3, 3 to 4, and back from n to 1. Kn is Hamiltonian. Can I add one vertex and make the graph not Hamiltonian? Let me ask the easy question. Can you add one vertex, and here's the hint, and no edges, and get a non-Hamiltonian graph? Yeah, of course. It's disconnected. There's no chance of Hamiltonian. What if you'd take a large complete graph, add one vertex and one edge? Still no chance of having a Hamiltonian cycle, but a Hamiltonian path, you can find that. Okay, what if you take a large complete graph, take 1 point and add 2 edges, like that one over there? Is that Hamiltonian? Yeah. So those have a lot of edges. Can you find a graph? I want you to find a graph, and one that we've looked at before. Find a graph that has what you would consider a lot of edges. That's not Hamiltonian. Wow, it got quiet. Talk to your buddies. That's why you have people at your table. Well, that's why some of you have people at your table.
So graph with a lot of edges, not Hamiltonian.
Graph with a lot of edges that's not Hamiltonian.
Yeah.
All right, let me. I'm just keep throwing them out at you. Can you come up with a complete bipartite graph? What is? Wait a second. What's a bipartite graph? Two independent. The vertex set can be partitioned into 2 independent sets. Okay.
So it can't be complete.
Why not? Wait, can you come up with a complete bipartite graph that has a lot of edges, and you decide what a lot of edges means? That's not Hamiltonian. Yeah, remind me again, what's a bipartite means what?
Partition into 2 sets.
The vertex partition into 2 sets.
If there are no adjacencies between vertices within one of the sets.
Okay, so I'm going to partition the vertices into 2 independent sets. So think about it. Let's see. So here's my graph, and I'm going to draw it,
Yeah.
就是 complete 白方它就是2个 set，
Okay, so here are my two pieces. Let's say there are m vertices here and n vertices here. That's a lot of edges, right? Let's see. Can you tell me how many edges are in the complete bipartite graph? And we know what this name is. The name of this graph is KMN. Well, let's start with how many edges are in the complete bipartite graph.
S. You could just move the S down to the bottom row.
M.
In that case.
M times n edges. Every vertex on the top is adjacent to. That's supposed to be an M on top, right? Every vertex on the top is adjacent to all n vertices on the bottom. So how many edges does it have? Let's see, that first vertex, that's n edges. The second vertex, that's n more edges. The third vertex, that's n more edges. The mth vertex, that's n more edges.
N squared.
And, okay, if they were both n, then it would be n squared. If I have m times n, then it's mn edges.
Yeah.
Is that always, there's a lot of edges there. Is that always Hamiltonian?
So only when
Are we guessing? Can you give me, so let's wait a minute.
so one of them must be odd. No, must be even. So then we can be.
Oh, one of them must be, one of them, because they differ by one?
Yeah. Well, because it's a bipartite, so every time you go to the bottom part,
Uh-huh.
you have to come back.
Right?
So
So,
So the number of elements must be the same,
oh, what?
right? You go down, up.
yeah.
Oh, this is a theorem. I'm thinking this is a theorem. Okay, so for this to be Hamiltonian, m must equal n.
Yes.
And now, what if I said, if and only if it's equal? Can you prove, so what do you have to prove if and only if? So if m and n are not equal, is it Hamiltonian? Can't be Hamiltonian. And now I'm going to use, wait a second, what was that graph that I put up at the start? Let's see, so I think that's a red graph. I have a rectangle around two vertices. And when I remove those two vertices, how many pieces do I have? When I remove these two vertices up here, how many pieces do I have when I remove those vertices?
3.
So there's no way that I can start here, come down to one of these pieces, go up there, come down to one of these pieces, and pick up this point, or this set of points. So if I remove two vertices, I can't have, in a Hamiltonian graph, I can't have three pieces. So now I'm ready for KMN. KMN, where M, let's say, is strictly less than N. The question is, can that be Hamiltonian? Okay, so let's see. When I remove the M vertices, how many pieces are left?
Did you say M or N?
When I remove the M vertices, and M is less than N, how many pieces are left? N pieces. Okay, so to be able to pick up all of the pieces, all of the N pieces, I need to have at least as many vertices on the top. So, for example, let's make it even clearer. K45. I can draw that. It's got nine vertices. 9 vertices, 4 vertices, and 5 vertices. And the question is this Hamiltonian? No.
No.
Why not? We just talked about this. When I remove the top 4 vertices, how many pieces are left?
5.
5 pieces. So there's no way I can have a Hamiltonian cycle that goes through all 9 vertices. So now can you give me I won't even call it a theorem, a thing about complete bipartite graphs and when complete bipartite graphs and when they're Hamiltonian? like, almost sounds like theorem, except it's just a thing, because we're not going to call it a theorem. When is a complete bipartite graph, KMN, Hamiltonian?
So, well, when we need to mention that if we just get rid of 4 pieces and 5 pieces left, not just m equals to n.
No, so if I get rid of if I get rid of 4 points and I have 5 pieces left, there's no way, if I get rid of 4 points, here are the 4 points. And just imagine I have 5 vertices left, 2, 3, 4, 5. Is there any way that we can have a Hamiltonian cycle? So one more time, blue only goes to red, and red doesn't go to red. Okay, so if I remove 4 vertices and I have 5 pieces, there's no way that I can have a Hamiltonian cycle. Yes?
Yes.
Okay, you see that?
Yeah.
Okay, so in general, where's general? In general, KMN? What? For it to be Hamiltonian, it must be the same. Okay, so for Hamiltonian, it must be the same. What if I don't care about the cycle? What about if I only want a Hamiltonian path? So traceable. Hamiltonian path. What about M and N? So they can be 1 apart. Okay, so if they were 1 apart, like m minus 1 and m, then what would you do? Where would the Hamiltonian path be? Careful, where would we start? Bottom. Got to start at the bottom. Okay, so if the 2 parts differ by exactly 1 vertex, then it's questions? Oh, I thought I said something funny. Okay, so if M and N are differ by 1, it is traceable, but if they differ by 2, yeah. Okay, so now you want to go back to this picture on page 208, and think about what about here it's asking for a Hamiltonian cycle or a cycle that contains all the vertices. What condition would we need to have for there not to be a Hamiltonian path? Okay, one more time. 208. That's where we're removing 2 points and leaving three pieces. So look at 208, the picture, look at that graph. Is there a Hamiltonian path? HP. Hamiltonian path, HP, question mark. sure? Anytime I ask you like that, you go,
Yes.
wait, you said no. Which one is it? Okay, it's only got 5 vertices. Does it have a Hamiltonian path? There's only 2 possible answers. Yes or no? No? You sure? Let me label the vertices. Oh, he's got it labeled. I'm going to use a different labeling, I'm sure. X1, X2, X3, X4, Y1, Y2. Does this graph contain a Hamiltonian path? One more time, a path that contains all the vertices. It does. Oh, wait a second, let me ask it this way. It does? What is the Hamiltonian, what is the path that contains all the vertices? I thought I heard someone was going to start. Path that contains all the vertices. Or maybe not.
Yeah, so we can start with XE,
So start with which one?
X1,
X1.
and then X2,
There you go. X2,
and then it's Y1,
Y1, X3,
Y2,
Y2,
X4.
X4. Great. Okay, so it's not Hamiltonian, but it is traceable. So what I want you to be thinking about is when a graph, what do you need for a graph to be traceable? What do you need for a graph to be Hamiltonian? Can you find graphs with a lot of edges that are not Hamiltonian? I'm going to give it the other way, and this one should be easy. Can you find graphs with very few edges? What's the fewest number of edges in a Hamiltonian graph? Let me ask it a different way. How many edges do you need for a Hamiltonian cycle? N. Okay, are there graphs with a few edges, more than n maybe, that are Hamiltonian? Are there some with few edges that are not Hamiltonian? Okay, so you're looking for different sets of graphs that are either Hamiltonian, not Hamiltonian, traceable, Hamiltonian path, or not Hamilton, does not contain a Hamiltonian path. We're going to talk about that. And finally, just like Eulerian, there are conditions that imply that a graph is Hamiltonian. Okay? It's not as easy as Eulerian. You can't get much easier than Eulerian. Hamiltonian is a little bit more difficult. See you Thursday.
So I was thinking with this path,
With
with this one,
Uh-huh.
I think there's another way we can show that it's not
Okay.
Hamiltonian, which is these two vertices have degree 2.
Oh, yeah.
So those have to be used.
Yeah.
And then right there, there's
That's a foresight,
C4,
yeah.
so we can't get it.
absolutely. That's it. Good.
你刚刚说的是 Friday 我还有别的事情，周六也是，我这个周末排练让他们，所以
你乃是这个整个春假都很满啊。
Yeah, and I just confirmed that I sent it to you last week. I
Okay.
sent it to you a couple days ahead of time, so I don't know.
Okay,
if
I'll get it.
春假之前的也是，不仅是周末，还有周一到周五。